So we're in physics unit 6 and we're talking about momentum, and we're working with the law of conservation of momentum. So we're at the top of page 3 and we're starting example 2. A football player of mass 90 kilograms is traveling at 7 meters per second and meets head-on another player of mass 120 kilograms traveling at 4 meters per second. They collide inelastically, and this is a term that means they stick together. So they are coming towards each other, they hit, and they stick. Find the velocity of the players after the collision. So first, let's draw a picture. You're always going to want to draw a picture in physics just to make sure that we're doing this right. Get in the habit, write your pictures in the notes, draw your pictures on the homework, draw your pictures on the test. There's really no circumstance where you should not draw a picture. So let's look at the before conditions. Now, a football player is a person. In physics, we just treat them like objects, and really there's no need to make your picture overly complicated. So here is your player of mass 90 kilograms, and he is traveling at 7 meters per second. The other player is mass 120 kilograms, so we'll draw this circle a little bit larger. This player is traveling at 4 meters per second, and he's moving in this direction. And the reason I know that is because they are meeting head on. If their velocities were in the same direction, they wouldn't collide for quite a while. And so this player has a velocity of 4 meters per second, but the velocity is in the opposite direction, which means we have an opposite sign. So this larger player has a velocity of negative 4 meters per second. After the collision, here's what happens. Here's our 90 kilogram player. Here's our 120 kilogram player. And they are colliding inelastically, which means when they hit, they're going to hit and they're going to stay together. Find the velocity of the players after the collision. So they're going to have some velocity, and that's what we're looking for. So I'm just going to say that they're going to have a velocity of x meters per second for the sake of my picture. Now, I drew it off to the right. It's possible that they will move left after this, but we don't know that right now. Until we do the calculation, we actually don't know what their speed is, and we don't know what the direction is. So for the sake of our picture, I put the x going to the right because that gives it a positive sign as far as the symbol is concerned. So we're going to use our formula for the law of conservation of momentum, where it was mass of A times the velocity of A plus the mass of B times the velocity of B, and that equals the mass of A times the velocity of A prime plus the mass of B times the velocity of B prime. So we can go ahead and put in the numbers that we have. So the mass of player A, 90 kilograms. The velocity of player A, 7 meters per second. Plus the mass of player B, 120, times the velocity of player B, -4. Equals, so now we're looking at the after conditions. The mass of player A is still 90. The only thing we don't know is his velocity. VA prime, we just know it's x. Plus the mass of B, which is 120, and the velocity of B prime is also x. So we're going to go ahead here and solve for x. 90 times 7, so 9 times 7 is 63. 90 times 7 is 630. Plus 12 times 4 is 48. 120 times 4, this is -480. And this is equals 90x plus 120x, 210x. So to simplify, 630 minus 480 is 150, and that equals 210x. Divide both sides by 210. We see that x equals 0.714 meters per second. Now for the direction here, the picture does not really give us an idea of the direction. But look, the velocity at the end is positive, and that's why I wanted it to be positive in my picture, because I don't have to change the sign here. So this positive velocity tells me that we are moving off to the right. Let's write a sentence for this one to help us. So their velocity is 0.714 meters per second. And here's the direction. In the original direction of the 90 kilogram player. So it wouldn't be very good for us to say the velocity is 0.714 meters per second to the right. In my picture, yes, that's how it's represented, but I could have just as easily put the 120 kilogram player on the left and the 90 kilogram player on the right. And so left and right doesn't really give me an indication. But this is sufficient in the original direction of the 90 kilogram player. In my picture, player was moving right, and now both players are moving right. Had I flipped my picture, it would have matched up the same. Example 3. A loaded semi rear-ends a car traveling in the same direction. The semi has 20 times the mass of the car and was traveling 3 times as fast. Find the final speed of the vehicles after an inelastic collision. Remember, inelastic means they're going to hit and they are going to stick together. So let's draw a simple picture here. Before. my semi of mass 20 times the mass of the car. Here's the car with mass m. The semi is moving 3 times as fast as the car. So let's say the car has velocity v, and the semi has the velocity of 3 times v. Make this velocity vector a little bit shorter, a little more representative. So here are my initial conditions. After the collision, this is an inelastic collision. So there's 20m, and there's m, and they are moving off with a velocity of x. And the question says, what is the final speed of the vehicles after an inelastic collision? So we're using the law of conservation of mass, the law of conservation of momentum, and the formula is up here, and that's a really long formula to be recopying for every example, every homework question. So we're just going to go straight into it and start putting in the data. So for the before, we have the mass of the semi, 20m. And we have the velocity of the semi, 3v, plus the mass of the car times the velocity of the car. After the collision, the mass of the semi is still 20 meters, and it now has a velocity of x. That's what we're looking for. Plus the car with a mass m, and it now has a velocity x, because in an inelastic collision, they are going to stick together, and move off with the same velocity. So here's what we're going to do. So this is, let's write all the steps. 60 mv plus mv equals 20 mx plus mx. And so we can simplify these things. This is 61 mv equals 21 mx. So as we look at this, we have mass on both sides, this m, and so we can cancel out these m's. And we have 61v equals 21 times x. So we divide both sides by 21, and you find that x equals, and this would be 61 over 21 times v. But in this class, we don't want to leave anything as fractions. And so putting it in the calculator, 61 over 21, 2.90 times v. And we don't know what the actual speeds were at the beginning. We don't know what v actually was. But here's the answer. Their final speed is 2.9 times the original speed of the car. So a little bit extra. So if we put in some concrete numbers, and let's say that the car had been traveling at 21 miles per hour, so that's the V. If it had been traveling at 21 miles per hour, these would cancel out, it would suddenly accelerate to 61 miles per hour, while the semi would decelerate from 63 to 61 miles per hour. The effect on the semi is very small, but the effect on the car is very large. The law of conservation of momentum doesn't just work for the examples that we've seen so far. It works for other things. It works for elastic collisions. Elastic is what we call bounce apart. So the two objects collide and they bounce off. It also works with inelastic collisions, which are what we've been working with. These are the ones where they hit and they stick together. It works with any number of objects, not just two. It works with 2, it works with 3, it works with 20, any number. It also works with any angle of collision. So it doesn't have to be a head-on collision. It can be, they could be coming in at an angle. They could be at 90 degrees, any angle. It could be any type of collision. Some later on topics, it could be magnetic, it could be electric, whatever the reason behind it was. And it also could be any size of objects. Could be objects as small as atoms. It could be objects as large as a star. Example 4. 2 carts, one 3 times as massive as the other, collide in a head-on, inelastic collision with equal speeds. Find the velocities after the collision. So this is an inelastic collision, so they are going to hit, they are going to stick together. That's always an important piece of information in the question. What type of a collision is it? So let's draw our picture. So before, 2 carts, one is 3 times as massive as the other. So here's 3m, and here's m. They collide in a head-on, inelastic collision with equal speeds. So head-on tells me about the direction. They're going towards each other. And equal speeds, so we'll say that this mass 3m has a velocity v, mass of m has also a velocity v, but it's in the opposite direction, so the sign is the opposite, so it's negative v. After, this is what it looks like. Here's my mass 3m. Here's my mass m. Here's the new velocity x. Find the velocities after the collision. So we're going to use the formula for the law of conservation of momentum. So object A is going to be this one, the more massive cart. Mass is 3m. velocity is v, plus cart B has a mass of m and the velocity of negative v. Equals, and this is the conditions after, we have three m times x plus m times x. So this is really 3mv minus mv, which is 2 times m times v. And on the other side, we have 3mx plus mx, 4 times mx. So this is a lot like the previous example. We have m as a factor on both sides. They can just cancel out. And so we have 2v equals 4x. Divide both sides by 4, and we find that x equals 1/2 the velocity. Example 5, 2 carts, one twice as massive as the other, colliding head-on in an inelastic collision. Before the collision, their speed were equal. After the collision, they traveled in the direction of the more massive cart at 1/3 its original speed. This says, show that this collision is consistent with the law of conservation of momentum. Before we do anything, we need to draw our picture. So before, we have 2 carts, one is twice as massive as the other. So here's 2m, and here's m. They are colliding in a head-on collision, which means they have velocities in opposite directions. They are both coming towards each other, and it says their speeds were equal. So this one has velocity v. The second cart is in the opposite direction, so the sign is opposite, but the speed is equal, so negative v. After, and we're talking about an inelastic collision, so they're going to hit and they're going to stick together. Here are the 2 carts, and what this says, after the collision, they traveled in the direction of the more massive cart, which is to the right, at 1/3 its original speed. So 1/3 times v. So let me fix this a little bit. This vector would be significantly shorter. There it is, and it is 1/3 times v. We're using the same formula, law of conservation of momentum. So object A is the more massive cart. 2 times m is the mass. Velocity is v. plus object B is the less massive cart of mass m, and its velocity is negative v. Those are the before conditions. And in the after conditions, we have a cart mass 2m, and its new velocity is 1/3 v, plus second cart mass m, its velocity is also 1/3 of the original velocity. And this is a show that thing. This is a math proof. And so we're not going to move anything from one side to the other. We want to make sure that this side actually equals this side. So 2m times v, and write that as 2mv, negative mv, so minus mv, where the negative minus came from, equals, this is 2m times 1/3 v, or 2/3 mv, and here we have positive 1/3 times m times v. And so what we have here, 2mv minus mv, is just mv. And 2/3 mv plus 1/3 mv is just mv. And so checks out.